Good afternoon, ladies and gentlemen. My name is Kleber Silva. I'm a professor at the University of Brasilia, and I'm here to present the paper titled Phasor Estimation Algorithms based on the discrete Hartley transform. I have been doing this work with my colleague Francisco Nascimento, who is also from the University of Brasilia. So it's well known that phasor estimation process plays a major role in modern numerical relays. In fact, digital filtering algorithms must provide bandpass response about the fundamental frequency, good transient behavior, harmonic elimination, and decay indice component rejection as well. The decay indice component is harder to deal with indeed, and it causes an undesirable error in phasor estimation outputs, leading protection scheme to misoperate. For example, distance protection either underreach or overreach the fault point, whereas overcurrent protection may lose selectivity. In order to overcome these drawbacks, modifying DFT-based phasor estimation algorithms have been widely used in real-world application. Even so, we do believe there is still room for improvements. That's why we are here to propose a new phasor estimation algorithm based on the discrete Hartley transform that present advantage over some DFT-based ones regarding the decay indice component rejection. So the discrete Hartley transform was widely used in the past as an alternative way to compute the discrete Fourier transform coefficient. By using the DHT, we can reduce the computational burden in this computation. However, as the time goes by, with the improvements of the fast Fourier transform algorithm, this transformation has not been used for this purpose anymore. So here we present the basic formulation of the discrete Hartley transform. This transformation uses as the base function the function CAS that comes from cosine plus sine, or cosine minus sine, depends on the argument of this function. So by using this basis function, we can apply the windowing process to compute the discrete Hartley transform coefficient in its complement. So even though this transformation has not been used for the reducing the computational burden on computation of the DFT coefficient, it's important to highlight that this transformation may provide different filtering characteristics, as one can see here by the analysis of the frequency response of the half-cycle filters and the full-cycle filters. As one can see here, these filters have a quite different frequency response. For example, they have a quite different side lobes for interharmonics, and for example, they have different gains for DC component in the case of half-cycle filters. So these filters, the filters from the discrete Hartley transform, are different from those used in discrete Fourier transformer. And we also highlight here that as the same as DFT, the DHT, the discrete Hartley transform, may also be applied along with the decimation process, in such way that we can also calculate the discrete Hartley transform coefficients using the decimation by 2 and using the decimation by 4. Actually, this is the key idea underlying the proposed algorithm, as one can see next. So here we present briefly the proposed algorithm that takes into account that the sampling process, the whole sampling process, is continuously performed by the relay in such way that the analog signal is firstly filtered using the anti-aliasing, a low-pass anti-aliasing filter before it becomes digital data. In such way that whenever we have a new sample acquired, the data window is updated, and then we firstly calculate the DHT coefficients for the even and odd sample set obtained from the decimation by 2 of the data window. And then combining these outputs, we can calculate the real and imaginary parts of the phasor using this equation here. But it's important to mention that these coefficients in red are dependent on the parameter lambda. Lambda, in fact, it's equal to the inverse of the exponential term of the decaying DC component. So in order to compute the parameter lambda, we first apply an additional stage of filtering. We use a first order digital low pass filter in order to reduce the impact of the decimation process. Actually, whenever we use a decimation process, the scheme as a whole becomes more sensitive to noise. So in order to reduce the sensitivity to noise, we apply this additional filtering process. Then we apply a decimation by 2 and a decimation by 4 in this filter data, and then apply the discrete Hartley transform for each one of these data set. And we combine these outputs in order to compute the parameter lambda. And now, using the parameter lambda, we can calculate the coefficients C, D, E, and F. Thereby, we can obtain the real part and imaginary part of the phasor without the decaying DC component effect. So, it's important to highlight, it's important to point out here that the proposed formulation can be applied for both full cycle and half cycle data window interchangeably. So we don't need to change nothing except the data window length. So we change only the data window length using the same formulation, and then we can calculate the fundamental frequency phasor without the decaying DC component effect. So we're gonna present some results next. Firstly, we present the transient response of the proposed algorithm applied to a full cycle data window and a half cycle data window, and compare their performance with the performance obtained using two other algorithms, two DFT-based algorithms reported in the literature on the subject. So here we plot the performance of the estimation of the amplitude, of the magnitude of the phasors, and as one can see here, for example, we can see that the proposed algorithm using the full cycle in blue and half cycle in red provides the smaller overshoot and the fast settling time. In fact, as one can see here, the proposed algorithm is able to quickly reach the fault steady state point, and there is no oscillation, there is no error after that. On the other hand, the DFT-based algorithms that we evaluated here present quite oscillated estimation here. So these kind of errors may lead the protection function to misoperate. So here we present a massive data analysis. This is a quite simple analysis indeed, in which we performance of an analysis varying the time constant of the decaying DC component and observe the maximum overshoot obtained. As one can see here, once more, the proposed algorithm provides the smallest overshoot, mainly the full cycle discrete Hartley transform algorithm. I mean, the proposed algorithm applied to a full cycle data window. So, as a conclusion, we may say that this paper is the first to present the use of the DHT in phasor estimation immune to the decaying DC component. And also, the proposed algorithms provide a smaller overshoot and settling time than some DFT-based algorithms reported in the literature, especially those ones that we evaluated here. And last but not least, the authors do believe the obtained results are preliminary, such that further analysis have been done to even more improve the performance of the proposed algorithm. So, thank you for your attention, and I'm open for comments and questions regarding this paper.
Hello everyone, my name is Rodrigo Medeiros and my presentation at workshop on communication networks and power systems is entitled Performance Assessment of a Wavelet-Based Differential Protection Scheme in the Interturn Fault Detection in a Transformer. So the main issue addressed in this paper lies in the fact that the interturn fault detection is still a challenge for traditional power transformer differential protection schemes because the transformer load current in these faults in general can be confused with the fault current. Uh, as an example, we can see uh, this figure. This figure illustrates an internal fault involving few turns on the wire winding, and there is almost no difference between the magnitudes of the currents before and after the fault initiation. Furthermore, the sensitivity of the traditional phase differential unit decreases significantly with the increase of the transformer loading, and the conventional algorithm usually detects interturn faults at a severe stage, and this fact can be dangerous for the power transformer health. So all these limitations of the traditional power transform differential protection can be overcome with the application of the wavelet transform. In order to give support to the previous commentary, recent works in literature proposed the use of the new wavelet differential units as a replacement of the traditional phase and negative sequence units. For example, these new wavelet units are named as 87TW and 87QW respectively. And this paper presents an extensively comparison between the performance of these two new differential units, new wavelet differential units, and their respective conventional ones regarding the detection of interturn of several interturn faults on the both sides of the power transformer for different power transformer loading scenarios. The existing wavelet-based differential protection, according to Medeiros 2018, runs with the following steps. The preprocessing, where the sampling rate used is equal to 15.36 kHz. And following, the wavelet transform is applied directly on the currents. The version of the wavelet transform is real-time boundary stationary wavelet transform, where the dB4 model wavelet is used. Uh, Another routines, the phase magnitude adjustments, differential coefficients, differential energy, and the application of the new wavelet units, the phase and negative sequence differential protections. Uh, All these steps are similar to steps verified in conventional techniques. The only difference lies in the fact that this method uses the high frequency components of the current transform currents instead of the conventional techniques that use the low frequency components obtained by a phase estimation process, for example. The simulated databases in this paper were turn to turn and turn to if faults on the Y winding, as well as turn to turn and turn to with faults on the delta winding. So all these faults were simulated by considering a variation of the percentage of the turns from 1 until 98%. Also, the angle delta of the remote source was varied with delta from minus 35 degrees until minus 65 degrees in order to investigate the system load variation effect. As results verified in this paper, firstly, a comparison between the wavelet and traditional phase units for a light load condition for delta equal minus 35 degrees. The wavelet unit presented a success rate of almost 100% with an average time delay of 0.1 milliseconds. On the other hand, the phase unit presented a success rate of only 81.89% with an average time delay of 15.29 milliseconds. For the negative sequence units in light load condition, uh, the wavelet negative sequence unit presented a success rate of 100% with an average time delay of 0.4 milliseconds, and the negative sequence traditional unit presented a success rate of 95.41% with an average time delay of 38 milliseconds. For heavy load conditions, the wavelet phase unit presented success rate of 98.72% with an average time delay of 0.4 milliseconds, and the traditional phase unit presented a success rate of only 68.62% with an average time delay of 80 milliseconds. Regarding the negative sequence units, for delta equal minus 65 degrees, that is in heavy loading conditions, the wavelet negative sequence unit presented a success rate of 99.23% with an average time delay of 0.67 milliseconds. On the other hand, the traditional negative sequence unit presented a success rate of 91.33% with an average time delay of only 40 milliseconds. That is bigger than 2 cycles at fundamental frequency. The performance summary of the wavelet and conventional units studied, analyzed in this paper. For the wavelet units, in general, the wavelet negative sequence unit was the best, presented 100% of success rate on light and medium loads. For the conventional units, the traditional phase unit was strongly affected by the load system variation. This unit presented a success rate of only 68.62% for delta equal minus 65 degrees, and the negative sequence unit was less affected, presented success rates varying between 95.41% and 91.33%. All the results verified in this paper are summarized in the table 1. As conclusions of this work, 2 points deserve special attention. That is efficiency and time delay. And in general lines, the wavelet differential protection scheme was quite efficient, faster, and independent of system load variations. The bibliography used in this presentation. Thank you.
Hi everyone, I am Luis Fernando Gontijo. I am honored to be here and present my research today. My article to the WCNPS 2020 is called Segmentation and Entropy Coding Analysis of a Data Compression System for Power Quality Disturbance. This presentation is divided into 6 sections. First, the signal data bank used in simulations. Second, the voltage and current signal coding system. Third, the dynamic bit allocation algorithm. Fourth, the segmentation window analysis. Fifth, the entropy coding analysis. And sixth, some conclusions. The signal data bank is composed of 60 voltage records and 36 current records. Voltage and current signals are sampled in 256 times per cycle of the fundamental frequency. Each sample has 16 bits in a 60 Hz distribution system. Both voltage and current signals have intake composition, several disturbances such as voltosegs and harmonics. Only the A phase of the voltage and current signals were used for the simulations. The sampling rate of the system is 15,360 samples per second, and the simulation carried out into work run in the databank present in the reference improved transient data compression algorithm based on wavelet spectral quantization models. The voltage and current signal coding system is shown by the diagram and was first proposed in the paper called Improved Transient Data Compression Algorithm based on wavelet spectral quantization models. The first stage of the discrete time segmentation of the input waveform by a window of size and samples. The second stage applies the discrete wavelet transform. The third stage quantizes the transform coefficient with a dynamic bit allocation algorithm. The fourth stage is the entropy coding of the quantized coefficients. The fifth and final stage is the data packing. The coding is the reverse process of the encoding. The first stage starts with the unpacking of the encoding data file, allowing access to each encoding segment. The second stage, the entropy is the entropy decoding of each frame. The third stage applies the inverse quantization, obtain the transform coefficient of each subband. The fourth stage consists of the inverse discrete wavelet transform. Finally, the fifth stage concatenates each segment of the coefficient obtained to generate the reconstruction waveform. The segment waveform, yeah. The quantization done by the dynamic bit allocation was first present in the paper called Improved Transient Data Compression Algorithm based on wavelet spectral quantization models. The process allocates a bigger number of bits for coefficients with higher energy levels and low frequency. Those carry great amount of information for the transformed signal. The DBA algorithm take into account the spectral envelope of the transformed signal, then choose the number of bits for each subband. Each coefficient with the same subband of the transformed signal is quantized with the same number of bits. The coefficient in the approximation subband is quantized according to the first equation of the slide, and where Bm is the number of bits of the subband at the m level. In the equation, Xmax is the maximum absolute value of the transformed coefficient. The other subband's coefficients are quantized according to the second equation, where uppercase M is the number of subbands in the transformed signal, lowercase m is the subband that is being quantized using the mi-m coefficient, and D indicates the transform coefficient that is being quantized in the mth subband. Here, just an illustration of the quantizing process. The coefficient in the first subbands are quantized with Bn equal to 4. The orders coefficient in the order subbands are quantized according to the distribution of the fixed spectral shape. This fixed spectral shape has different ways to be projected, but thus are always the crescent curve limited with theta max and theta min. Theta max indicates the maximum quantity of bits given to sample in a certain subband, and in the same way, theta min indicates the minimum quantity of bits given to samples in a certain subband. For the example in the slide, theta max is equal to 16 bits and theta minimum is equal to 4 bits. This section analyzes the different size of segmentation windows in the encoding and decoding system. Window size equal to 256, 512, 1024, 2048, and 4096 samples was used. The results obtained in this section used the wavelet family of the 5. The fixed spectral curve used is the decreasing exponential. And in addition, Hoffman entropy coding, while used in the literature, was applied. The initial value of theta max and theta min was 16 bits and 15 bits respectively. The figure shows that the compression rate results for different signal-to-noise ratio levels obtained for different segmentation window size. Each point of the figures indicate different levels of theta max and theta min. For the first point, we have theta max equal to 16 bits, and theta minimum is equal to 15 bits. For the second point, we have theta max equal to 15 bits and theta minimum equal to 14 bits. And so on until theta max is equal to 7 bits and theta minimum is equal to 6 bits. As observed in the figures, the compression rate is higher for higher segmentation window size, considering each SNR levels. This is due to the less space needed for lateral information. The figure in the slide confirm its hypothesis. The decrease of overhead information beats proportion while the segmentation window size increase, favoring the compression results for large segmentation windows. Now, in this section, we analyze the influence of entropy coding algorithm used in the entropy coding stage of the encoding system. For the simulation, we used Hoffman coding, arithmetic coding, and the context-based arithmetic coding. This algorithm uses each symbol probability of occurrence given observation of the previous symbols. The idea here is in this algorithm is to use the bias in the series of coefficients present in the input signal vector. For the simulations, in this analysis, we use the configuration of the code and decoder system. The window size used in the simulation is equal to 1044 samples. The results obtained in the section used wavelength family of the 5. The fixed spectral profile curve used is the decreasing exponential 2. And for the entropy code stage, we use the three possible coding algorithms: Hoffman, arithmetic, and context-based arithmetic coding. The initial value of theta max and theta min are 16 bits and 15 bits respectively. As observed in the figures, the context-based arithmetic coding algorithm have better compression ratio values for different signal-to-noise levels. Given the context in which the symbol is encoded, each has greater probability of occurrence. This way of calculating the cumulative probability of symbols occurrence makes better updates in the coding intervals, presenting a more effective version than the conventional arithmetic coding algorithm. Since the signal used in this work are mostly sinusoidal, except for intervals with disturbance, the context-based arithmetic algorithm tends to show good results. This is due, of course, to the good symbol prediction when observing the symbol that occurred previously. Some conclusions, just greater signal compression was observed for the same SNR levels when large segmentation window size was used. For the entropy coding algorithm, it was observed that the context-based arithmetic coding algorithm showed higher compression radius values at the same SNR levels. This improvement is a result of most of the input signals being sinusoidal. The knowledge in memory of the statistical characteristics of each encoding coefficient provides better values of cumulative probabilities used to update the coding limits in the arithmetic coding algorithm. Finally, some alternatives for future studies related on the representation system are the implementation of different entropy coding algorithms and the recursive coding of several signals in the same file. Thank you. And this was the reference used for the research, and thank you for your attention.
Hello everyone, my name is Felipe Lopes. I am from the University of Brasilia and I am here to present the paper Electrical Noise Simulation, a Practical Approach for ATP Draw Studies. This paper has been developed in partnership with my colleagues Nilo Ribeiro from Eletronorte, Gustavo Cunha, Tiago Honorato and Professor Kleber Silva from University of Brasilia. This paper is motivated by the increasing importance of transient-based power system monitoring functions. Indeed, a lot of high-speed protection and fault location algorithms have been reported in the literature and also embedded in actual devices which analyze instantaneous values and traveling waves in time domain. In this case, the analysis of high-frequency components is of utmost importance, and so the electrical noise influence can be critical because they can distort the signals as shown in this figure here. So, a way to evaluate the electrical noise influence during the development of time domain functions, the use of real systems waveform that contain already noise present in the waveforms is a good choice. However, real records are not always available in such a way that the way to best represent these transients is using electromagnetic transient program called here EMTP programs. Even so, even when we use EMTP programs, we have noticed the need for electrical noise simulation directly in the simulation platform in such a way that in this paper we propose a solution to emulate noises in the alternative transients program, which is a type of EMTP program that has been widely used worldwide. When we do not have real-time simulators available, the ATP can be used to simulate power systems in order to test real devices. To do so, playback tests based on contract files generated by ADP are used. And looking towards the simulation of noise, we can think that the emulation of electrical noise directly in ATP environment could be a good choice. However, to do so, the model's language available in ADP environment would be required to be used. But this programming language, it's the routines implemented using this programming language are applied dynamically during the simulation, and this language has a reduced number of functions in such a way that emulating electrical noise by means of these routines could be not practical. Another way to think about noise simulation, considering signals taken from ADP, is to export ATP records and use external programming or mathematical platforms in order to create noise signals and then to export them directly to the device to be tested. However, in this case, we would need to generate constraint files, which is also a task that can be complicated for many people, and depending on the format of these contract files, the format required to build these files. So the proposal in this paper consists on interacting the ADP with the MATLAB program, which is considered a good mathematical platform with promptly available functions that are capable of simulating electrical noise. Then we take these noise signals, import back into ADP environment, which is then responsible to generate constraint files that can be used to test real device. This is our main goal here. And the proposed solution is divided into 3 simple steps. The first one consists in the electrical noise generation. Basically, we here simulate the power system using the ATP draw. So we have as a result the sig-in, which is a signal without noise. Then these signals are imported into MATLAB, where we use this very simple routine here to add a white Gaussian noise into the input signal sig-in. To do so, we consider an user-defined signal-to-noise ratio, which is proportional to the measured power in the input signal, considering a given seed random stream to generate this noise. And so as a result, we have the signal sig-noi here. And then by subtracting the noisy signal with the sig-in from the sig-in from the noisy signal sig-noi, we can estimate a pure noise signal, which is called here noise. This procedure is also performed in MATLAB environment. Then, in the second step, we take this noise signal and we upload its samples into the empirical source type 1 available in ATP draw in such a way that we can reproduce into the ATP environment the obtained noise signal. Finally, we just take this empirical source and we connect the source into an emulation noise circuit in which we take the signals from the system and the noise signal. We transform these signals into tax variables in order to allow their superposition, and then we take the obtained noisy text signal into a system signal by means of tax source. So we can do this procedure, we can carry this procedure out to voltages and currents the same way, just paying attention to the types of this source you are using. So to demonstrate such an application, we considered a transmission line modeled in ATP draw, and this transmission line was modeled considering real data taken from a line in operation in Brazil, and in each line end we connected the noise emulation circuits in order to add noise to voltages and currents. And then we simulated also some faults in order to illustrate a practical example to which the proposed approach could be useful. So here we illustrate some results. We can see that by varying the signal to noise ratio, we indeed emulate different noise levels as expected, so that we can control these noise levels, varying the case from only a slight noise case to very critical noise case here, as you can see here. And finally, just to demonstrate a practical applications example of traveling wave studies, if we consider a signal, a fault record here taken from a current transformer. If we consider a zoomed area here, we would see in the microsecond time scale some steps, and these steps are related to the moment at which traveling waves reach the monitor terminal. So in practice, we have in the market today some device that use a filtering process to extract traveling waves information, which respond to step change as a triangle shaped outputs. And when we consider different noise levels, we can see that the noise presence can affect the visualization or even the detection of these transients, which are usually required by many traveling wave based solutions. So as conclusions, we can say that the proposed approach takes advantage of the ADP transient simulation functions. Indeed, EMTP tests are the most realistic ones that can be carried out in today's technology. Existing MATLAB electrical noise simulation functions are also taken into account so that we can simulate different signal to noise ratio values from the measured input signal power. And as a final conclusion, we can state that the proposed approach is useful for tests in real device, tests in ATP draw models, and also to reproduce real noise into the ATP environment. So we really believe that the proposed approach can be useful for many research around the world. So that's it. Thank you for your attention.
Hello everyone, my name is Anderson de Araújo. I'm going to present the work Transient Voltage on Lighting Protection Systems with Stratified and Damaged Conditions. The other authors are Walter de Azevedo, José Anibali, and José Pissolato, and we are from Unicamp. Ground systems are essential to provide safety during thunderstorms. So, an accurate ground system model is required to compute the electric potential rise. In this context, vertical and horizontal electrodes that compose this ground grid system can be represented by transmission line theory, and then a lumped representation is obtained using the vector fitting technique. In this paper, we are presenting transient currents and voltages are investigated for a real LPS, lighting protection system, which is subject to a lightning strike. We consider these conditions for homogeneous and stratified soils, and the condition that the ground system is perfect, in the meaning like whole, and damage, when there is a rupture in one of the conductors. First, we have a general representation of a LPS system, which is formed by an upper grid, lighting rods, down conductors, and the ground grid, which is horizontal and vertical electrodes. For modeling the down conductors, we are using the component line ZT in ATP software. The upper grid is modeled by transmission line JMRT model, and the vertical electrode, when we consider stratified soil, we use these formulas here to compute the equivalent soil resistivity, and then we compute the admittance and apply the vector fitting technique, which representative circuits is obtained. For the horizontal electrode, use these equations to calculate the parameters using the pi section representation, and each segment, the length of each segment must respect this criteria over here, lambda over 10. If we guarantee that condition, we can represent this electrode by a lumped circuit. As numerical results, we have here first a test, like the validation. So we have this system, LPS system, which we apply a lightning current at the corner, and we measure the currents in 8 different points. Here is our reference, which is explained in the article, and here are our results that we obtained with our model. And then when we represent horizontal electrodes by the lumped circuit theory that was explained before, we have homogeneous soils and stratified soil, which we apply the transmission line theory to compute the impedance, and we can see here the both response when we have the transmission line theory and then when we apply the lumped circuit theory. And here we have the impedance, and then we have the magnitude and the phase. So we can see here both models they match perfectly from that frequency range here. Then our model will be studied using the upper grid represented by J-Marti transmission line model, Dow conductors represent for single transmission lines, and the ground grid system as horizontal and vertical electrons. Here are the parameters, geometrical parameters, the soils, so two conditions. So when we have homogeneous soils would be 1000 ohm meters, and when we have stratified soil 1500 meters. And other details you can check in the article. First, just one thing more, so we also consider the whole condition, so there is no rupture here in the ground system, and then we apply a rupture that these dashed lines here, and this point is disconnected from the ground system grid. First, we analyze the currents, which is the currents in segments A prime and A and AB. So I will just return here. So it would be that current here, and then the other current flowing that direction, considering the whole system condition and the rupture when this damage. So we can see here when the whole condition we have these currents, but as we have the failure, the damage condition, we have the current AB, they increase significantly. This is for the homogeneous soil, and then when we have the stratified soil, we can see they present lower peaks in comparison for the first case, but they present similar behavior as in the damage condition. They almost are the same currents. This is explained because in this condition, in the stratified soil, the soil resistivity is lower than the first case. So it is expected to have lower currents. Now we are considering the voltage in 5 points different along the grid. So it would be the points A, B, C, D, C, and D along the grid, the ground system grid. So we return here, we have in this condition for homogeneous soil, we have almost 900 kilovolts in this condition. And here, when we have the rupture, we see for the first case, they increase up to 1200 kilovolts. And then when we have the stratified soil, we have lower peaks in comparison with the homogeneous soil. But even though when we have the damage condition, they will present the highest peaks. To summarize here, we have put all the data in a table, so we can have how to quantify the magnitude of these peaks. So we can see here when we have the rupture, the current increase in for the segment AB, they increase for the normal and the rupture condition significantly in some for both scenarios. Concerning the voltage, we can see like the point A prime, they have present a significant variation. This variation is computed considering the hole and the damage condition. So the reference you can see here. So for the homogeneous soils, the point A and the point D have present, we highlighted these values, and then when we look at the stratified condition, they also present the significant, like the highest and the lowest values for the points, for all the points studied. As conclusion, the lumped parameter can be used to represent horizontal and vertical electrodes and be incorporated in ATP software. The currents have presented a significant variation in damage condition. Transient voltage present a pronounced increasement in the damage condition, and as advantage of this approach, we can represent any arrangement of ground system and consider the frequency dependence on the soil parameters and other layers of soil and ionization effects that can be considered using the lumped representation for the grounding system. I would like to thank you to FAPESP, CGTI, and Unicamp. Thank you.